Hello everyone and welcome to the new episode of our series of solving LeetCode Daily challenges. And today we are going to solve a problem called smallest sufficient team, which is a hard problem. And yeah, as I said yesterday, on this channel we enjoy hard problems because we love to make these hard problems relatively easy for you guys. And that's exactly what we are going to do today. So without further ado, let's move to the problem statement. So we have some project and we have a list of required skills to complete this project. We also have a list of people and we know what skills do each person have. And we need to consider a notion of a sufficient team. A team is called a sufficient team if it consists of a set of people such that for every required skills in this rec skills, there is at least one person in the team who has that specific skill. And we can represent this team by the index of each person. We need to return any sufficient team of the smallest possible size represented by the index of each person. We may return the answer in any order, and if there are several such results, we can return any of them. Let's look at the constraints. So the first constraint is a really important one, is that the number of required skills is less than or equal to 16, which immediately leads us into thinking that maybe our solution should contain an exponential term in terms of required skills lengths. So yeah, and actually that's what's going to happen. So all of the required skills consist of lowercase English letters, they are quite short, and they are all unique. The total number of people is less than 60. The total number of skills that a person can have is less than or equal to 16. And yeah, this skill length is also quite short. All of these strings that represent skills consist of lowercase English letters. They're all unique among a single person, and every skill in that person can have is also mentioned in this required skills array. And it's guaranteed that a sufficient team exists. And yeah, that's pretty much it. So how are we going to approach this problem? So we have an optimization problem on our hands, and whenever I see an optimization problem, I immediately think of dynamic programming. And sometimes it's possible to apply it, sometimes it isn't. Well, in this case, it is possible. So let's define a recursive function. We will call it solve, and it will return the lowest possible number of people that can be in this sufficient team. And we need to maintain some state in our function, and we will maintain two values in our state. The first one is person index, and it basically tells us that, okay, currently I'm looking at a person with a certain index, and I have already processed all of the people with smaller indexes. And the second variable in our state is skill set, and basically it tells us what skills we have already acquired from either picking the previous people to our team or skipping them. Okay, so what are the base cases for our recursive DP? So suppose we have already acquired all of the skills, then there is no need to continue and add people to our team, and we can say that from now on we need to add 0 people to our team. Okay, suppose that it's not the case, that we have not acquired all of the skills, but we have already looked through all of the people. In this case, our recursive DP has failed, and we need to signal it to our recursive calls. And we will do it by returning infinity, because our problem is minimization problem, and if we return something very, very, very big, it means that something went wrong, and that's what we are telling. The next condition is very important for every single recursive implementation of dynamic programming. And if we have already processed a state of person index and skill set, then let's just return the cache value. Okay, we have looked at all of the base scenarios, now let's look at our recursive transitions. We have exactly 2 recursive transitions. If we are considering a person with index person index, then we should either include him or her to the team or skip him or her. So, and that's exactly what we are going to take a look at. So our first transition is about skipping a person, and these transitions us to a state of person index plus 1, because now we will consider the next person and exactly the same skill set. And our second transition is when we decide to include this person to our team. So this takes us to the state of person index plus 1, because once again, we will take a look at the next person, but we will also join the sets of our current skill sets that we have and the skill set of this specific person. Unfortunately, this doesn't come for free, because yeah, we have added a new person to our team, so we need to add 1 to this specific recursive transition. And our result will be just the minimum among these 2 specific transitions. For now, we do not care what our team will look like, we only want to know what will be the size of this team, and we will return to figuring out what exactly is this team later on. Okay, for now, let's think about this second parameter in our state, which is skill set. So how are we going to maintain a set? Of course, we can just literally use a set, which is a data structure that we have in pretty much every single good programming language, but it will be too slow in this case. It might work, it might get accepted, but there is a way for a very well-known optimization, and we will call it bitmasks. And yeah, everyone calls it bitmasks. So a bitmasks is a very convenient way to maintain a set with a given basically maximum size. So if we know that the total size of a set is limited, and we know that basically the set okay, I need to think how to tell it correctly, so I will tell it based on this example. So here, let's look at this all skills array, and it contains of 3 elements: Java, C++, and Python. And yeah, basically we have a limited number of elements that can be present in a set. Yeah, that's a good definition. And we need to represent some sets that can be only subsets of this set of all skills. Suppose we have some person that maintain 2 of these 3 skills, Java and Python. We will represent this subset of our set all skills as an integer, but we will look at this integer not in a decimal form as we have basically usually do. Instead, we will look at it in binary form. And in binary, each bit in the number is either equal to 1 or 0. And suppose our subset contains some value, some skill in this case, with index I. In this case, the bit with index I of our bitmask will be equal to 1. And if our subset does not contain this element with this specific index, then the bit of the bitmask with this specific index will be equal to 0. So for example, if we have this all skills and person skills, we want to represent this person skills as a bitmask. So our person skills contains the skill with index 0, therefore its bit with index 0 is equal to 1. It doesn't contain the skill with index 1, therefore our bit with index 1 is equal to 0. And it does contain the skill with index 2, and therefore our bit with index 2 is equal to 1. So we have a bitmask that looks like this in binary, 101, which is equal to 5 in decimal. And that's exactly how we are going to maintain this skill set variable. It will be equal to a bitmask, and we will represent it as an integer. Okay, the last missing piece in our solution is to figuring out what the team is. So we know how to find out what the size of the team, but how do we find out what are the actual people that are included in this team? So yeah, to do that, for each state of our dynamic programming, we will store not only the result in the cache, we will also store how have we achieved this result. So we will store what the optimal transition was, and it can be either skip a certain person or take it to the team. Then we'll be able to restore the answer. And I will show how it works in a minute. So let's look at the code. Today's solution is in C++ because yesterday I was asked to write a solution in C++. And I'm sorry guys, my C++ is far from perfect. I haven't coded in it in a while. However, I was able to make this code work, and let me show you how it works. So first of all, we are going to build people skills. And by this, I mean that for each person, we will build its mask that will tell us what skills does this person has. Okay, so let's look at this method. So we are going to create a map that will basically tell us an index for each skill, and it's really easy. We will just iterate through all of the skills, and we will tell that for a specific skill, its index is basically its index in the array of required skills. And then we're going to iterate through all of the people, and then we're going to iterate through all of the skills for this specific people, for the specific person, and we will just add this skill to set with some bit operations, which I'm not going to focus on, but I will leave some useful links in the description of this video so that you guys can take a look how it works. Okay, so, but the important part is that for each person, we are going to have a bitmask that will tell which skills does this person have. Okay, and we're going to store it in the array called people skill in a vector. Okay, we did that. Then we have set some variables. Then we have prepared the cache, which is a simple method that just returns a vector of a needed size. We have also prepared another array in which we are going to store this way that we have chosen in a specific dynamic programming state, and it will help us to restore the actual team later on. And then I'm simply calling the recursion. So let's take a look how this recursion looks like. So we have a recursion with two parameters. If we have acquired all skills, then we return 0. And to check that, once again, we are using some bit operations that I'm not going to explain right now, but I will link necessary materials. And if all skills acquired, we return 0. If not all skills acquired, but we have looked through all of the people, we return infinity. If we have already been in the state, we return the cached value. Otherwise, we calculate two results. The result for keeping the current person and the result for taking the current person. The transitions are exactly just like I explained a couple of minutes ago. And then we compare our results. If the results for skipping this person is less than the result for taking this person, then in our way vector, we tell that, okay, we are skipping this person, we store this result in cache, and we return it. Otherwise, in our way array, we store that we are taking this person, we cache this result, and we return it. So all pretty straightforward. So we have called our dynamic programming from index 0, which means that currently we will need to take a look at the first person, and skill sets of empty mask, which basically means that currently we do not have any skills. And in the end, we will return the value of the method called restoreResult. Now that we have launched our dynamic programming, we can actually tell what people will be present in our team. So to do that, we will need to maintain the current set of skills that we have already acquired, and this vector interest will basically maintain the result, the indexes of people that will be a part of our team. So we will iterate through all of the people, and we will take a look. If we have acquired all of the skills, then we can break. Then we will take a look if we have included this person to the team. Then we will add the index of this person to our result, and we will transition to the next state. Just like we did in our dynamic programming, we will call exactly the same method with exactly the same parameters. And it is necessary because this will help us to correctly restore the result and correctly transition between states. And in the end, we just return the list of the people that we have acquired. And that's it, guys. So what's the complexity of this solution? So all of our transitions take big O of 1 time to complete. So we just need to calculate how many states are in this recursion. And let's take a look. So this person index can be anything from 0 to people lengths. So it's basically big O of people.lengths times. And now we need to find out how many possible skill sets are there. So there are no more than 16 possible skills. And basically our question is how many subsets of a set of a size 16 there are. And there are no more than 2 to the power of required skills lengths such subsets. And therefore that's our complexity. And in the worst case scenario, it's something like 60 times 2 to the power of 16, and that's something that we can easily fit in the time limit. Okay, guys, thank you for your attention. This problem was a hard one. I hope you enjoy my explanation. If you did, please press like and subscribe. It's really, really important for me. If you have any questions left, feel free to ask them in the comment. I will try to answer them all in a timely manner. Thank you very much, guys. Have a nice day. Bye-bye.